Okay, so let's start talking about the power bus. Okay, so the power bus or the power supply for this board is basically what we're going to have is we will have a wall connector here. Okay, this is going to be connected to the 120 volt wall outlet, right? And there's going to be a cord that's going to come over to our board. Okay, and on the board there's going to be a barrel connector on the board. That's one of those little standard circular barrel connectors that you see on a lot of electronics. Okay, and this is going to create 12 volts DC. Okay, DC just means that it's the power supply is always at 12 volts. Okay, so usually there's going to be two conductors. Usually you have a center tap, which is the inside. If you look at the barrel connector head on, the inside of the barrel connector is going to be plus 12 volts, and then the outside of the barrel connector is going to be, we're going to call that ground, okay, or 0 volts. Okay, cool. So yeah, so we have two conductors, 12 volts and ground. All right. And if you look at the, if you stick your oscilloscope on this thing, okay, you're going to see that, if I can make a plot of the voltage versus time, okay, on the 12 volt bus here, okay, this is the voltage on the y-axis and time on the x-axis, you're going to see that it's not, it'll be approximately 12 volts, but it's not always going to be exactly the same, right? There might be, half a volt of ripple. Okay, this is called power supply ripple, right? And chips don't like power supply ripple. Chips like to have a flat voltage that's exactly exactly whatever voltage they call for. Right? All the chips that we're going to be using on this project are going to be 5-volt chips. Okay, so what we need to do two things, right? The first thing we need to do is we need to get a solid 5 volts, right? We need to step our 12 volt input down to 5 volt output so that we can actually supply power to our chips. And we need to make sure that we don't have too much ripple on our 5 volt bus, okay? So for the first thing, we're going to use a thing called a voltage regulator, okay? And as the name sounds like, it basically is going to regulate the voltage, right? It just makes sure that we always have the same voltage, 5 volts on our power supply. Okay, and the voltage regulator, it's called a 7805. Okay, 7805 UA 7805, and it looks kind of like this. It's got 3 pins. It's in a TO2, this is called a TO220 package, right? So the first pin is the input, that's going to be 12 volts. The second pin is going to be ground. The middle pin is ground, and the output is going to be, this is the output, that's going to be 5 volts, okay? Okay, perfect. So basically the way this is going to work is you're going to hook your 12 volts and your ground from your barrel connector up to the first 2 pins, and you're going to hook your ground and your output up to the second 2 pins, right? And the output, this is going to go over to our 68,000 microprocessor, and to our all these different chips, our memory, and etc. Okay, it's going to be the power supply for all of our stuff. Okay, perfect. Love it, right? So this is a voltage regulator. The voltage regulator takes an input voltage, the higher input voltage, like 12 volts or 9 volts or whatever. It might be a little bit ripply or whatever. It might have some ripple, and it puts out a solid whatever voltage, 5 volts or whatever it is. Okay? So the ripple is a problem in these digital circuits, right? So the regulator can only regulate so much, right? So let me explain one of the major problems that we have in digital circuits. So you probably heard of the clock, okay? When you say you have for example, my laptop is a 2.3 gigahertz chip, right? That means that the clock oscillates up and down 2.3 billion times per second, okay? On this, on our Homebrew computer, our clock is going to be maybe 10 megahertz or so, something like that, right? So it'll be 10 million times per second. The clock is going to go up and down, okay? And every time the clock goes through a complete cycle, right? That's a rising edge to rising edge. This is one complete cycle of the clock. Then every time we move to the next cycle, every time we go to the next rising edge, then the state of the chip changes and it starts doing some other thing, okay? Whatever that might be. If it's executing an instruction, it moves on to the next instruction and maybe it fetches some data out from memory or something like that, right? Right? And so when it changes state, so it always changes state on rising edges. I don't know why they picked the rising edge. It could have been just as easily could have chosen the falling edge, right? But for some reason, we always change state on the rising edge of the clock. Okay, and so it so happens that the transistors inside of these chips, they only really consume power when they're changing state. Okay, so what does the power consumption profile of this chip look like? Right. Let's draw it out. Power consumption on the y-axis versus time on the x-axis. Right. So we're going along. We're not using very much power, and as soon as we come to a rising edge here, what's going to happen is the power consumption is going to shoot way up, okay? Because all of my, internally, all my circuits are going to be changing state, right? And then, it'll decline a little bit as the, as the cycle moves on, and there'll be less things changing state in the middle. And then as soon as we come to the next rising edge, bam, shoots back up again. Power consumption is huge, right? And then falls back down, right? So every time we have a rising edge of the clock, we have a huge rush of power consumption, okay? And what happens is it tends to cause, if we look at the voltage on our 5-volt bus, right? That's what's happening is that's causing a lot of demand for current, okay? So if we look at the voltage on the 5-volt bus, what's happening is if we don't do anything, it's going to cause the voltage to dip a little bit every time we have a transition. Okay, and I'll explain why that is in a second. Okay, and if you zoom out on this, basically the upshot here is if you zoom out on this thing, this looks like voltage ripple, right? This causes this causes voltage ripple, which is bad. Okay, we don't like voltage ripple. Okay, so we need to correct for this, right? And so the voltage regulator can correct for this to some extent, but it's not. It can't do a perfect job. Okay, so let's talk for a second here about how voltage works. Okay, so everybody knows if I have let's say I have two positive charges, right? So everybody knows that positive charges like to repel each other, okay? So they're pushing against each other, right? Like charges repel each other, right? Opposite charges tend to attract each other, and like charges repel each other, okay? And, you have Coulomb's law, which says that the force on two positive charges is kind of like proportional to the charge, the product of the charges divided by the distance between the two charges, right? The distance is kind of like the separation, okay? And this is basically what creates voltage, right? So let's say it's this Coulomb's law thing that creates voltage, right? So let's say we have a wire. So here's my wire. Okay, I'm going to zoom way in on this wire. Here's the end of it. And I'm going to put a couple of positive charges on this wire, okay? So here's a positive charge, and here's a positive charge. I have two positive charges on this wire, and they're pushing against each other. Okay? All right. So let's say I have a third charge, right? It's outside of this wire, and I'm going to bring it in. I want to put it on the wire. Okay, I have a third charge that's outside this wire. I want to bring it onto the wire. So these two charges, if the third charge is far away, right? The force on this third charge coming from these other charges is fairly small because the third charge is far away. But as I move this third charge onto this wire, closer to the wire, the force on the third charge due to the other two charges increases, right? Because the distance gets smaller. As the distance gets smaller, then the force goes up, okay? And so the amount of work that I have to do to push this from outside the wire to inside the wire, I have to do some work to push this charge from outside the wire to inside the wire, okay? And finally, once this charge is inside of my wire, then I've had to do some work to get it there, okay? And the work that I've had to do to get the third charge from outside the wire to inside the wire is energy, okay? So energy of the third charge is basically just equal to the amount of work that I had to do to push it onto the wire. Okay, let's say I have a fourth charge. Let me erase my lines here. And suppose I have a fourth charge that's outside the wire, okay? So basically, let's say how much energy do we have to start with here, right? So these three charges are on this wire. Let's say I have 1 unit of energy here, 1 unit of energy here, and 1 unit of energy here, okay? Now if I have a fourth charge, the amount of work that I have to do to push this fourth charge onto the wire is more than what I had to do to push the third one on, right? Because now instead of having 2 charges on the wire that are repelling this fourth charge, right? Now I have three other charges that are repelling it, okay? So I have to do like 1.5 times as much work to push the fourth charge onto the wire than I did to push the third charge on. Okay, so if I push the fourth charge onto this wire, okay, the amount of total energy on the wire has gone up, right? Because now instead of 3 charges, now we have 4, okay? But the amount of energy per charge has also gone up because now I have 4 charges, repelling one another. Previously, I only had 3, okay? So the energy goes up as I increase the number of charges on the wire. Okay, this is the energy of the charge, the total energy of the charges, right? And also the energy per charge also goes up. Okay, because now I have 4 charges that are mutually repelling each other instead of 3. Okay, and this energy per charge, this thing is called voltage. Okay, and this is the thing that we can measure when we use an oscilloscope, or if we use a voltmeter or something like that. We're actually measuring the energy per charge on the wire. Okay. And basically the voltage is caused by charges being next to each other, right? Positive charges don't like to be next to each other. They like to be far apart as possible, okay? But if I take some charges and I cram them all on the same wire, then that creates additional energy. It pumps the energy up and it pumps the voltage up. Okay, that's how voltage is created, by cramming positive charges next to each other. Okay, great. So, but the problem is, the problem that we were talking about before was this energy consumption of a chip, right? Where basically the power consumption, right, basically spikes around clock edges, right? So every time we have a clock edge, let's do a more realistic drawing of a wire here. Whoops. I'll make a more realistic drawing of a wire. It's not just 3 charges on my wire. I have many, many charges on this wire. Okay, so here's my charges that live on my wire, okay? And the total amount of energy per charge is going to be proportional to the number of charges, right? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I have 12 positive charges on my wire right now, okay? And when I come to a rising clock edge, what's going to happen is basically some of these charges that are on my wire are going to get pulled off by the circuits that are on my board. Okay, so now instead of having 12 positive charges on my wire, now I only have 10. Okay, so now I only have 10 positive charges on my wire. Okay, and so that means that the voltage, let's say, has gone from, we'll call it the voltage caused by 12 charges, right? Or we could say 12 volts here, right? To 10 volts. Okay. Okay, so we've had a reduction. We've had I'll say roughly maybe a 20% or 16% or so reduction in voltage because we pulled some charges off this wire. Okay, and the voltage regulator, its job is the whole voltage regulator's job in life is basically to cram two more positive charges onto this wire, so that we can bring the voltage back up to 12 volts. Right? But the voltage regulator is way far away, right? So it's going to take a while before these charges can propagate from way far away over to where they need to be here next to these other charges in order to prop the voltage back up to 12 volts, okay, or to 12 positive charges, right? And in the meantime, basically what's happened, if we make a plot here, this is the same plot as we made before, right? We started out at 12, right? And then as soon as we had a rising clock edge, we took a couple off and we drooped down to 10, right? And that's going to stay there for a while until the voltage regulator has a chance to pump some more charge back onto the wire and prop the voltage back up to 12, okay? And this is what happens every time we have a rising clock edge. The circuits on our board are going to consume some power, and that's basically going to what happens is that takes the form of pulling these positive charges off of the wire, and in response our voltage regulator will pump some more positive charges back onto the wire to take their place. But the problem is that it takes a while for those positive charges to get from the voltage regulator over to right next to the circuit. Okay, and in that time it causes this voltage droop. Okay, and this is bad. Okay, so what are we going to do about this, right? Okay, so suppose if you think about this wire, right? One way you could kind of think about this wire is kind of like a hallway, right? If you've ever been in a crowded hallway before, people are standing right next to each other, and if a couple of people leave, what we've just been saying here is if a couple of people leave, the hallway is going to get much less crowded, okay? And which is going to cause the voltage to go down, right? Which is what we don't want. We don't want the voltage to go down, okay? So what we can do instead is we can put like kind of a little room off to the side of this hallway. Let me just draw it like this. Oops. I'll draw it like we have a little room over here. Okay, off to the side of the hallway. And in that room, we have a bunch of other positive charges that are all sitting there too. Now this is right next door to our chip. So, so these guys are all relatively close by to each other. Okay? So now we got this room with these positive charges that are inside, and we're going to have another. Well, let's see what happens when we take two positive charges off of this thing. So first of all, let's count the total number of positive charges that we have. 21. Okay, so we got 21 charges in our whole system here. Okay, so what's going to happen is if we take two of these guys away on our if we take two of these charges away from the from the wire, right? Then we're going to go from having 21 positive charges to 19. Okay? So that's only, that's less than a 5% reduction in voltage. Okay? Because previously, we went from having 12 positive charges to 10 positive charges, right? Which was like, we'll say a 17%. I don't know exactly what it is, but let's say a 17% reduction in voltage. okay? And we got this improvement. So this is a big improvement, okay? So the amount of ripple that we're experiencing here is much less now that we created this room off to the side, right? So basically what we did is we just added a little bit of extra wire, a little bit of extra space for these positive charges to spread out in, okay? So in a circuit, what that space is called a capacitor. Okay, so a capacitor is a circuit element. A capacitor is a circuit element that stores charge. And it's basically a reservoir for charge, so that when we have a chip, right, if we have some kind of a chip over here that's consuming power, right, then as that chip, if we have rising edges of the clock on this chip, when it has these rushes of influx of power on it, it won't cause the voltage to dip down on the power bus every time we have a rising edge in the clock. Okay, that's what a capacitor does. So what we're going to do when we build our board is every time we put a chip, we're going to put a little capacitor right next to it. Okay, the capacitance that we usually use is called 100 nanofarads, right? This is the value of the capacitance that you need to put next to every chip. Okay, so I really shouldn't say every chip. It should be every power supply line. So if you have so some chips have more than one power supply line. So every power supply line that the chip has on it should have a capacitor next to it. So like for example on the 68000, I think there's 3 or 4 power supply pins. So you're going to need to have 3 or 4 100 nanofarad capacitors next to that chip. All right, let's get after it and actually build something now. So here's my board that I'm going to use. They got this thing from Janeco. This is, I think, an 8x5 board. Okay. So on the top surface, you can see there's no metal or anything like that. This is where the components are going to go. And on the bottom side, you can see that there's some, every hole has a little pad around it. Okay. This is where we're going to solder our wires. So the pins are going to stick through the bottom to this side. Okay. You can see that I have stuck some standoffs on this guy. These are a little too short. I'm probably going to replace these with some longer ones eventually. This is all I had on me right now, so we'll go with these for now. But you're going to want to put some standoffs on this board because you're going to have some wires down here, and you're going to want to have something to protect it when you set it down. You don't want to be putting the weight of the board on the wires below. Okay, you want to have something to lift it off the ground a little bit. Okay. Okay, cool. So let's take a look at this this pattern here of these pads. So you can see most of the pads. I don't know if you can see this on the video or not, but most of the pads have are sort of like independent islands that aren't connected to anything else. Okay, but if you look around the sort of like the periphery of the board, we have buses, right? So we have a big long bus on the top side, on both sides, and on the bottom, right? And you also have an I-shaped bus that goes down the center, and it also fans out to both sides here. Okay, so the ones that go around the edges, I'm going to use those for power, and the I-shaped one that goes down the center, I'm going to use that for ground. Doesn't really matter. You could switch that if you wanted to, but I'm going to do it that way. And but you should use those for power and ground, though. That's what they're for. This board was designed for making a homebrew computer, basically. So if you get a board that doesn't have, you don't need to have solder pads on your board. Okay, I've built these things before without any solder pads on the bottom. It works just fine. I think it's a little easier to use the boards that have solder pads on the bottom, because the chips will stick a little bit better. Your wires will stick a little bit easier to the back, right? But you could just as easily do this with a board that doesn't have solder pads or power buses on it. You just need to run wires. Typically people would run a big long wire down the edge. They'd have one going down one side for power and another going down the other side for ground, usually. And then you just kind of twist tie it to the board through the holes or something like that with some other pieces of wire. That'll work fine too if you want to do it that way. Okay, so that's what we're gonna do. So here's my barrel connector, right? And what you can see here is that I got the barrel connector that has small pins. Okay, and even these smaller pins were a little bit too big for the holes in my board, so I had to drill out a couple of the holes on my board here. to make these pins fit through, and that's fine. That's not a big deal. What you'll notice is I was careful to make sure that I did not attach these pins to the, I don't want to put any of my pins through the holes that go on this bus. Okay, I want to make sure whenever I put a chip on this board, I want to make sure that I stay away from these buses, because you don't want to connect all your pins together. Okay, unless you intend to do that, right? So we're gonna solder this guy on, all right, and then we're going to connect it to the input. We're going to connect the 12-volt pin on this barrel connector to the input on my input pin on my 7805. Okay, and that's going to go kind of like right next to it. So we'll keep that stuff over here on this side of the board, far away from everything else. And then and so the other thing we got to do here is this 7805. This thing's going to get hot. Okay. So we don't want to just leave it sticking up through like this, right? It's going to get hot. It might even overheat. So what we're going to do is we're going to kind of bend it over. We're going to bend it back so it's laying flat on the board here. And we're actually going to drill a hole through our board and put a screw in there. And we're going to screw this heat sink pad on this guy to the back of the board. And the board is basically going to act as the heat sink for this 7805 connector. You can even buy special metal heat sinks for the purpose of dissipating heat on these things. And if you want to do that, that's fine too. I don't think that's going to be necessary in this case. I think we can probably just use the board. I think that'll be fine. Okay, so let's get after it now. So the first thing we need to do is check this guy. You always want to check these power supplies to figure out what pin is what. Okay, so I have a supply here that's plugged into the wall. This is my barrel connector. This is going to plug into my supply like that. So I'm going to take my voltmeter here and I'm going to hook it up. I'm going to put it on the volt measurement setting, and I'm going to just check it. I'm going to stick the middle into the hole. Okay, and I'm going to put so the red one, this is the plus terminal, and the black one is going to be on the outside. And I'm reading 12 volts here. Okay, I'm reading 12 volts on my voltmeter. Okay, so what that's telling me is that the center tap, this is called center tap positive. So the hole of this thing is the positive terminal, and the shell on the outside is the negative terminal, right? So if I were to reverse these guys, if I put the black one in the middle and I put the red one on the outside, my voltmeter is going to read negative 12 volts. Okay, that means that I got my voltage terminals reversed. Okay, and so basically what that's telling me is that the voltage terminals are reversed. Anyway, point being, the center tap on this guy is going to be positive, and that's typical. Most of these things, most of these power supplies have center tap positive. Okay, so now I'm going to plug it into this guy here. Okay, and I'll just connect my pins like so, and it looks like I got the terminals reversed. So it looks as if the back terminal here is going to be the negative, and the back terminal is positive, right? So this guy toward the back, if you can see it, that I've connected my red one to, is positive. One toward my front is negative. Okay, and this third one on the side, that doesn't do anything. Okay, perfect. Okay, so 12 volts on back, ground on front. Let's hook her up. So I'll fire up the iron here and let it heat up. What we're going to do is we will just punch this guy through like that. And then I'm just going to put a little bead of solder on the pad for this guy. Okay. To hold him in place. And we're good to go. Okay, looks great. And now we will put this one on. Let's see. No, we don't want to put it, okay, so I put it on this first row here, but these are all three connected together, so I don't want to use that first row. I want to use the row right behind it. Okay, so this row right behind it, I don't know if you can see it or not, but basically these 3 pins are not connected. They're isolated by themselves. So we'll use that one. I'm going to bend it back like this. Okay. And then I need to check which hole to use. I think I already measured this out. This guy is a 9/64. So I'll put this in my drill real quick here. There we go. Looks great. So now I'm going to just use a screw. Screw that thing in and mount it. I'll make sure that's nice and snug on there. Okay. Looks good. Now let's solder this guy. Let's connect this thing to some pads here, shall we? Okay. Okay, so the pinout for this thing. We have input, that's going to be plus 12 volts. Ground in the middle. Output, that's going to be our plus 5 volts. Okay? Okay, here we go. So I'll begin by just, well, here we go. Let me get some wire here. So I'm going to use red wire for the power supply. Okay, so I'll take a piece of red here, like that, and I'm going to use it to go from the plus 12 volt side here over to my input. Okay, all right, so let me double check this and make sure I got the right voltage here. Can't check too many times. You definitely don't want to reverse the terminals on our power supply here, because that's going to cook our, okay, so 12 volts is in the back, okay? All right, 12 volts is in the back here. So this 12 volt line is going to go over here. This is our input, right? Okay, looks great. Okay. 12 volts is away from the board edge. What can we say? Okay. Okay, what did I do with my piece of wire here now? Okay. Let's see, what is this? 24 gauge or 22? Okay, so I always want to color code my wires here. When we're doing one of these things. Makes it a lot easier to figure out what's going on when you got a lot of wires running if you color code them. All right. So here we go. Let's heat this bad boy up here. Oops. Got that thing stuck in this. It's probably wasn't the greatest table to use. Probably Probably also better not work on it while it's on. Okay. Some of us ain't that bright though, huh? Okay, here we go. Okay, so that's my, oops, that's hot. That is hot, buddy. Right, this is how it's gonna go. It's gonna be a long project. Okay, there's my plus 12 volt input going to my input on my regulator. This wire could have been a little longer. Probably didn't cut enough wire there. There we go. I think that's a good joint. Okay. That's my input, and I want to make sure, I want to make absolutely certain that I am not touching the plus 12 volts to that outside bus, because I definitely do not want to apply 12 volts to that bus. Alright, let's make sure that's as far away as possible. Okay, there we go. Alright, I think that's pretty sure that's making contact there. Okay, here we go. Now ground is going to be right here, so we'll just use a little snip of wire for that, for our ground. I'm going to use, normally I am going to use black for ground, but I'm not even going to. Okay, so my video died on my GoPro halfway through doing this, so I'll just film it on my iPad instead. Anyway, here's the finished product that I ended up with after doing all that soldering. Hopefully we can see a little bit better close up here. So we got our 7805 screwed down to the board. We got our barrel connector, and I ended up adding a surge capacitor here. I'll talk about that in a second. Okay, so let's take a look at the bottom of the board here and see what we're doing. So first of all, I think you can get a little bit better view from this camera here, what the buses look like on here, right? So I have a power bus that goes around the periphery of the board here. Okay, you can see it comes down here too. And then in the middle, we have this eye-shaped thing. Let me zoom out a little bit. You can kind of see this eye-shaped bus in the middle here. And this is going to be my ground, okay? And all the rest of the pads on this board are independent, okay? So they're not connected to each other electrically. Okay, so this is a little difficult to see here, but you can kind of make out the pins from our power connector, right? Our barrel connector here. So the front is going to be ground. I've used black wires to connect that together, right? So we have a ground from our barrel connector is going over to the center pin on the voltage regulator, the 7805, right? If you can kind of see that there. Let's see here. So that's our center pin on the 7805. The rear pin, the one that's far away from the edge of the board, this is going to be carrying 12 volts. This is going to the leftmost pin on the 7805 if you're looking at it from the front, right? This is the leftmost pin, and this is the rightmost pin if you're looking at it from the front. So we have input, ground, and output of 5 volts, right? And I don't know how well you can really see that there, but I just put a little tiny jumper wire that jumps from the output pin on the 7805 over to this power bus here. Okay, so this is a 5 volt output pin. Okay, and then what we've done here is I have a wire that's going on the top. It's being run on the top of the board from the 5 volt bus here over to the 5 volt bus on the this other peripheral 5 volt bus here. Let's flip the board over. You can see this is my jumper wire that jumps those two together. Okay, and then I have the surge capacitor here that's going between the power and ground, right? And that's basically just adding some extra capacitance there. Okay, so if you look at the surge capacitor, before we cut the leads on it, you have a long terminal and a short terminal. The long terminal is connected to the positive side, and the short terminal is connected to the negative side, right? So long terminal goes to 5 volts, short terminal goes to ground, and we also have an additional indicator on here in case you cut the 5 volt or cut the wire short or something like that. You can see that we have a kind of like a minus sign painted on the side of this thing. That'll tell you which one is the negative terminal, right? That's going to go to ground. Okay, so so that's it's just going through the bottom of this board here, and you can see it's coming out, and I've connected it right here. Okay, so this is the plus 5 volts and the ground side over there. Okay. So, and then I've also run those same jumper connectors, those same jumper wires to connect the 5 volt buses on all of the peripheral parts of this, all the peripheral buses here. Okay. So there we have it. That's our power supply. We can plug it in. It gives us 5 volts, and I think that that'll look good. So next time we are on to the microprocessor.